Alright, welcome back. Math 1910. We're starting chapter 3 here. We're going to get into section 1. We're going to talk about extrema on an interval. So when we're talking about the word extrema, we're looking for, maximums and minimums. And we're going to be taking a look at what extrema look like on open intervals and what extremas look like on closed intervals. Okay, so we're really asking this question, does the function have a maximum value? Does it have a minimum value? And then we're going to kind of start focusing on where is the function increasing, where is it decreasing. Okay, so we're able to use derivatives and calculus to calculate all these. So let's first look at what the definition of an extrema is. All right, so let f be defined on an interval I containing c. All right, so we're going to define this for all functions. Okay, so 1, f of c, that's a minimum of f on I when f of c is less than or equal to f of x for all x in I. So, right, it's a minimum. It's less than the function, right? The f of c is. F of c is a maximum of f on I when f of c is greater than or equal to x. So notice that it has, both of these have the less than or equal to or greater than or equal to. So we are, able to look at the endpoints on the interval, okay? You guys can, kind of read through this as I kind of sum it up. But where we talk about the minimum and maximum of function on an interval, okay, they're also going to be called the absolute min and the absolute max. Okay, very rarely do we call it global min, global max, but it's also noted as that sometimes as well. Okay, the extrema can occur at endpoints on the interval. They can also, occur, between points on an interval as well. So if we have an extrema that occur at the endpoints, we call it the endpoint extrema. All right, so let's take a look at a couple of graphs here. It's the graph is identical here. It's x squared plus 1. But, things can change if we are on an open interval versus an open or a closed interval. So if we look at the graph on the left-hand side, figure 3.1a, okay, that's a closed interval. Notice we have brackets on -1, 2, and notice that the holes are filled in at the endpoints, so closed interval. If we look at the figure on the right, okay, that's an open interval because we are not including the endpoints. Okay, we use parentheses and we have open circles there. Okay, so if we take a look, both graphs have a minimum, okay, and a maximum on there. But if we look, the maximum does not occur on the open interval. Okay, it only occurs on the closed interval. On the closed interval, the maximum happens at the endpoint. Okay, the minimum occurs obviously there at the lowest point at 0, 1. So just note that the maximum is not going to occur or the absolute maximum is not going to occur on the endpoints. All right, we might have some local max or local mins or things like that. But if we take a look at the minimum, okay, the minimum does occur on the open interval. So understanding when we can include the endpoint as a maximum, okay, if we're on a closed interval, if we're on an open interval, we cannot include the endpoint as a maximum or a minimum if we're on an open interval. Okay, if we're on the closed interval, we can. All right, so, how does continuity affect this? Well, let's take a look at theorem 3.1. It says, if f is continuous on a closed interval, a to b, then f has both a minimum and a maximum. Okay, so if it's continuous, we will have a minimum and a maximum. That does not necessarily mean that it's on the endpoints, though. It can be the endpoints, okay? It may not be the endpoints. It might be in between, okay? So, the problem with this function is if we look and it's turned into a piecewise function, right? This is very similar to the last function that we looked at. However, notice there's now a hole there, okay? So that minimum does not occur at 0, 1 now. The minimum occurs at -1, 2, okay? If we have a minimum. We can have a maximum here, but since this function is not continuous, okay, we only have a maximum here. Okay, we don't have that minimum because that hole is at the minimum right there, if that makes sense. Okay, so continuity really affects, our maximum and our minimums. We must be continuous on the entirety of that function for it to have the minimum and the maximum on that interval. In this case, we only have the maximum on that interval. All right, because f of 0 is defined as 2. The function, right, the value does not equal the limit. If we were to take the left-hand and the right-hand limit of this function, we would be approaching 1. However, 1 doesn't exist. As we approach 0 from the left or right, the value is 2. As we approach 0 from the left and right, the limit is 1. Since the limit does not equal the value there, that's why we cannot have a minimum there, because the function isn't continuous there. Okay, so let's look at this function. We have what we call a relative min and a relative max. Okay, relative min and relative max. That means that there's a max and a min that occur on the interval, but they're not the absolute max, absolute min. Notice that if we look at this function, the absolute max can potentially go to 0. The absolute minimum can go to negative infinity. But we have relative maximums and relative minimums because this function is continuous. This is where we would have to define it on a specific interval to have maximums and minimums. Okay, so when we have relative max and mins, those are usually going to be like humps or hills in the graph and valleys or troughs. Okay, as we kind of go through and define those. So we're able to define if we have a relative min or a relative max, but it is also based on the interval. Okay, so this is an open interval, okay, and this function is continuous, from negative infinity to positive infinity. So we're going to be looking at relative minimum and relative maximum as we do this, okay? So, where do hills and valleys and things like that, okay? Okay, when we have a hill or a valley, okay, we have a smooth and rounded curve on the graph, not a V like an absolute value. So when we have that hill or that valley at that point, right, and we've learned this in previous chapters, when we take the derivative at that point, we have a horizontal tangent line, okay, so our slope there is 0. Okay, so that's how we can understand if we have a hill or valley. When the hill or the valley is a sharp point, right, like an absolute value, that function is not differentiable at that point. Okay, so we cannot conclude, okay, if it's a max or a min based on that. But if we have a hill or a valley, okay, we know our horizontal tangent line is 0. All right, so let's define relative extrema here. All right, so 1, if there's an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f. Okay? Or you can say that f has a relative maximum at C, f of C. All right? If there's an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum. Or you can say that f has a relative minimum at C, f of C. So notice what's the point on this one. Both of these are the open interval. So this goes back to a couple slides ago where we had that continuous graph from negative infinity to positive infinity, and we had the hill and the valley that's laying there. Okay, so just for clarification, if we talk about plural of maximum, all right, we have maxima, all right, so that's the plural of maximum, and then we have minima, which is the plural of minimum. We might have multiple minimums or things like that. Okay, so relative maximum, relative minimum, they're sometimes called our local max, local min. So if we talk about those terms, relative max, relative min, or local max, local min, those words mean the same thing when we're solving our problems here. So let's take a look at these three functions separately as we go through the next few slides here, okay? So on the left we have the graph f of x equals 9 times the quantity of x squared minus 3 divided by x cubed. Okay, so if we were to graph this function, okay, on the open interval, this function goes from what? Negative infinity, all right, and then it does have a relative max, and the relative max on this function could be the absolute max as well. Okay, but so in order for us to find that, we want to find when the derivative is 0. Okay, so how do we find that? So we take the derivative of the function, so that would be the quotient. We're going to walk through this in the next few slides, but we're going to find when the derivative is 0. Okay, so when the derivative is 0, that tells us what? There's a horizontal tangent line there. So if we notice the derivative of this function at 3, 2, the horizontal tangent line occurs there, all right, and the slope will be 0. Now if we look at the next graph, right, and we're going to go through these on the next couple slides, but as we look at the next graph, we talked about this, where we have a sharp point, right? That's a v, that's an absolute value. We know the derivative doesn't exist there, okay? It has a relative min there, okay, but the derivative does not exist. So we can't conclude any, other than relative min by examining the graph, okay? So we can't necessarily find it there. We're going to talk about that. That's going to be a critical number later. And we handle absolute values a little bit differently. And then if we look at the trig function, right, we have f of x equals sine of x. We know that if that's sine of x, okay, where we have a min and a maximum, we know that the sine maximum always occurs at pi over 2, or 90 degrees, right? That's when sine is 1. And we also know that the minimum occurs at -3, or at 3 pi over 2 when it's -1, okay, which is 270 degrees, right? So there's where we have a relative max, relative min, because the graph of sine function is continuous and it goes on forever and ever and ever. So we're going to have multiple relative max, relative mins. It's just going to be based on the interval that we're looking at. All right, so we're going to go through, I'm going to step back just one second here. So we're going to go through these three in a little bit more detail here. So we're going to go through A, B, and C. So the first one, A, if we take the derivative of the function, okay, so quotient rule, as we go through all that. I'm not going to go through step by step. We should know the quotient rule by now as we go through this. All right. Then when we simplify everything down, we're going to set this equal to 0 and solve for x. All right. So if we multiply both sides by x to the fourth times 0 is 0, and we'll essentially divide by 9, 0 divided by 9 sides. So we're left with 9 minus x squared, difference of two squares. All right. So we get a choice of, plus or minus 3 when we solve that problem. And obviously minus 3 is not in question here. What's in question is 3. So the solution for this is going to be, when is the derivative equal to 0 here? When x equals 3. So we have to see, right, that f prime of 3, so we're going to substitute in f prime of 3. When we put that in, the derivative is 0. Okay, so we know that we have a horizontal tangent line there. And when we plug in f equals 3, that tells us that there is a minimum or a maximum there. So when we plug that in, all right, when we take 3 and we plug it back into the original function, we get 3, 2. All right, so you're going to take that 3 and plug it back into 9 times x squared minus 3 divided by x cubed. All right, and you're going to get a y value of 2. So our relative maximum occurs at 3, 2. All right, and remember this one's difficult on this one because it's an absolute value function. So we know that it's not differentiable here at x equals 0. Right, because we have a sharp point. And remember, that was from, chapter 1 when we talked about limits, when the left-hand limit didn't equal the right-hand limit. Because if we take the limit as x approaches 0 on the left, all right, we get a slope of -1. If we take the limit as x approaches 0 on the right, we get a slope, all right, of +1. And since the derivative, the left-hand limit and the right-hand limit don't agree, all right, we know it's not differentiable at 0 here. So we just have to remember those sort of things. All right, so that's this piece right here. If we take a look at the limit from the left, the limit from the right, substituting in those, right, they don't exist. That doesn't exist. Since the left-hand limit and the right-hand limit doesn't exist, the derivative at x equals 0 does not exist. There's still a minimum there, but we can't define it because the derivative does not exist at 0. All right, so let's look at the last one. We have the derivative of f of x equals sine of x. Or I'm sorry, the original function is f of x equals sine of x. The derivative, f of x, equals cosine of x. So we have to find out, when is cosine equal to 0? Okay, cosine is equal to 0 at pi over 2, 3 pi over 2, and so on and so forth. Okay, so we know, sorry, I didn't mean to step forward there. We know that if we substitute in, pi over 2, into cosine, into the argument of cosine, we get 0. And if 3 pi over 2. That's where sine has a maximum, right? Sine of pi over 2 is 1, and sine of 3 pi over 2 is -1. So we talked about that before. So we can conclude when the derivative is 0, okay, we have a relative maximum, and we have a relative minimum here for the values of sine. All right, so we're able to conclude that when we substitute in pi over 2 and 3 pi over 2. So we get our relative maximum and our relative minimum. And we did that by setting the derivative of the function equal to 0 and solving for what values occur there. Alright, so just taking a look back at this. All right, if we have, relative extrema here, now what's important is we find what we call the critical numbers. Okay, the critical numbers occur when the derivative is either 0, all right, or the derivative does not exist there. So if we take a look at the graph on the left, okay, the point C here is a critical number of f. The derivative does not exist, right, because that graph comes to a sharp point, all right, which means the left-hand side limit and the right-hand side limit as they approach C don't agree. But it's still a critical number, which means since it's a critical number, we could potentially have a maximum or a minimum there. If we look at the graph on the right, C is a critical number, all right, because we're changing concavity. All right, f prime of C is 0 there, our horizontal tangent line. Our slope is 0. It's a critical number because we have a maximum or a minimum there. So when we solve for relative extrema, relative mins, maxes, we're looking for the critical numbers. Okay, so how do we define them? All right, let f be defined at C. So if f prime of C equals 0 or f is not differentiable at C, then C is a critical number of f. So we just went through those two cases, okay? So if the derivative is 0 there, or the derivative doesn't exist there, we can conclude that that's a critical number and that some sort of extrema occurs there. It could be a relative min, it could be a relative max. All right, so if we look at theorem 3.2, okay, relative extrema only occur at critical numbers. Okay, so if f is a relative minimum or a relative maximum at x equals c, then c is a critical number of f. So these two kind of intertwine, right? If we, when the derivative is 0, or when the derivative exists at that critical number, we're going to have a relative max or relative min there. Okay, so how do we find those? Very important, all right? We have to be continuous on a closed interval from A to B. So if we're continuous on the closed interval from A to B, okay, we're going to be able to first find the critical numbers of f in the open interval A to B. So what does that mean? That means we take the derivative of the function and set it equal to 0. All right, so these are important steps. Make sure to write them down. So step 1, find the critical number. We're going to take the derivative of the function, set it equal to 0, and solve. The numbers we get are the critical numbers. What do? We take those critical numbers and we substitute them back into the original function. Okay, we substitute the critical numbers. If we have 1, we substitute in. If we have 3 critical numbers, we substitute them back into the original function. Okay, so step 3, we're going to evaluate the endpoints on the closed interval A to B. So what's that tell us? Well, that's going to tell us if we have a minimum or a maximum on the closed interval at the endpoints, and it's going to also tell us if we have a maximum or minimum that occurs at the critical numbers, or where those occur. Okay, and then we're going to be able to define if we have a relative maximum or relative minimum. Okay, so let's do an example here. We want to find the extrema on the closed interval. So we have the function f of x equals 3x to the 4th minus 4x cubed, and we are on the closed interval -1 to 2. Alright, so first step, we are going to differentiate the function. Alright, so take the first derivative. Alright, then you're going to set the first derivative equal to 0. So in this case, you're going to factor out a 12x squared from both functions. Alright, so you're going to factor out a 12x squared from both functions. You'll be left with 12x squared times x minus 1. When you do that, you set each one equal to 0 when we do this. Alright, so when we do that, we set 12x squared equal to 0, so x will be 0, and we set x minus 1 equal to 0 and solve, and x gives us 1. So x equals 0 and x equals 1. Those are the critical numbers. So all we did was step 1. Okay, we set the derivative equal to 0 and solved for the critical numbers. Okay, so that was step 1. Step 2, okay, we have to, substitute in the critical numbers into the original function. Alright, so we're going to evaluate them, and then we're going to substitute in at the endpoints and evaluate. So when we do this, okay, I'm going to step back just one slide here. If we notice, the interval we're talking about is from -1 to 2. So we're going to plug -1 into the function, get something out. We're going to plug in 2 into the function and get something out. We're going to plug in 0 into the function and get something out, and we're going to plug in 1 and get something out. And I know I'm using plug-in, but you know what I mean. I mean substituting. Okay, so that helps us determine if we have a maximum or a minimum value. So the left endpoint, we substituted in -1. So f of -1, we put -1 into the original function, we get back a 7. All right, we substitute in our first critical number, 0, into the original function. When we substitute 0 in, we get 0 back. We substitute in our next critical number, f of 1. When we plug in 1 into the original function, we get a -1 back. All right, and then we have our right endpoint. We substitute in 2. All right, and we get 16. So we line these up in order, right? We have our left endpoint, our two critical numbers, all right, are in more numerical order of -1, 0, 1, and 2. This tells us when we have a maximum or a minimum on the interval. So we're able to look at that. And, just looking at the table we make, so when you guys do your homework assignment, it's going to make sense for you to make some sort of table like this so we can evaluate. So we can find the minimum occurs at what? 1, -1. That's the smallest value, right? So we know that the minimum occurs at the negative number, at the critical number of 1, -1, that's when we have the minimum. Okay, the maximum on this particular interval actually occurs at the endpoint. So f of 2, right? 16 is our largest y value here, so that's when our maximum occurs. So if we were to graph this function or sketch it, and we take a look at this sketch here, all right, and we plot the function, from -1 to 2, and we put all the values in, we can visually see now, all right, that this function has a minimum at 1, -1, and a maximum at 2, 16. So, there's how we're able to conclude and define those. All right, so notice, I'm stepping back a slide, we did have the other critical number, right? That was 0, 0, but notice at 0, okay, it doesn't give us a max or minimum. So just remember, the critical numbers don't always say that we have a max, that we have to have a max there, we have to have a min there. It tells us that a minimum or a maximum can occur there. Okay, so they're important points. That's why we call them critical numbers. Okay, so just kind of important when we take care of that and understand what a critical number means. It means that we could have a maximum or a minimum there on the interval. It doesn't mean that we're guaranteed a maximum or a minimum on the interval. So just remember that, all right? Taking the derivative, setting it equal to 0, solving for the critical numbers. Critical numbers can tell us that we may or may not have a maximum or a minimum there. The next step, evaluate the endpoints and evaluate the critical numbers. And then you need to analyze the endpoints and analyze the critical numbers that are substituted back into the original function and analyze them to see if you're yielding a maximum or a minimum that is occurring on that interval. Alright guys, well that's the end of this lecture. Let me know if you have any questions. Feel free to email me. Let me know if we need to Zoom meet or team meet or anything like that. Else guys, have a great day. I'll see you in class.